So now we're going to move on to Newton's laws of motion, the wonderful gems that Sir Isaac Newton gave us. You're probably familiar with them, might even be able to recite them from memory. Unfortunately, I've met a lot of people who can recite them from memory but who cannot apply them well. So they do seem pretty simple, but they're almost deceptively simple. I mean, it took humanity thousands of years to finally come up with these simple laws, and once they did, it kind of changed the world and ushered in the Industrial Revolution and all of that stuff. So Newton's laws are centered around this kind of main concept of force. So I like to define force simply as an interaction between two objects. Simple enough. Interaction. And by interaction, I mean a push or a pull between two objects. And why we need two objects is because you can't exert a force on yourself. Now you're probably saying, Mr. Giusti, you're crazy. I can punch myself or push my leg or something like that. Well, that's true, but if you think about if you were floating in interstellar space, weightless there in your spacesuit, if you didn't have some jetpack or something, there's nothing you could do to make yourself move. I mean, you can push on your leg, but that's not going to make you as an entire object start moving if you weren't already. Or if you're already moving, you can't stop yourself unless you touch something else. So we always need two objects because we're considering external forces is typically what we mean when we say forces. So not a force that you exert on yourself, because those don't really do much in the long run. They might hurt, but they're not going to change your motion. All right, and we tend to, I mean, we can just call everything a push or a pull, but a lot of times it's more useful to list forces by more specific names. For instance, one that we're all familiar with, even though nobody knows exactly how it works, is our good friend gravity. We have some other common forces would be things like friction, that which slows us down all the time. It also allows us to walk, so friction is our friend. Let's see, we also have tension is something we will be seeing often. By tension I mean like a rope or a pulley. Well, no, a rope over a pulley. A rope or a string holding something up. We also have what we call the normal force. And by normal, we don't mean average everyday force, we mean a perpendicular force. So these are usually surfaces supporting an object. Some people call them support forces, whether it's a table or the ground or something. Those forces are always perpendicular to the surface that's exerting it. We also have what we call drag, also known as air resistance. Drag gets a little bit complicated. It's usually dependent on your speed, so we won't look at that too much, but occasionally we might. Over here I'm also going to put electric forces. These are forces between charged particles, or if you have a collection of charged particles like the static on your shirt, that can hold your shirt together with forces, or rubbing a balloon on your head and sticking it to the wall. Those are electric forces. And we also have magnetic forces, obviously between magnets or electromagnets. And I wrote these in two columns for a reason. These forces over here are what we sometimes refer to as contact forces. And by that I mean that the two objects that are interacting have to be touching in order to feel these contact forces. Even air resistance requires you to be colliding with the particles of the air. These forces over here we can think of as long-range forces, meaning they can act over a distance even if they're not touching. If you jump up in the air, gravity will pull you back down even though you're no longer touching the earth. So there we have it, some common forces that we will be dealing with. And it is important to be able to identify the forces acting on an object to be able to figure out how they're going to influence that object's motion. So that's why this division is kind of useful. If I want to know, if I've got a box sitting on a table and I want to know what forces are acting on that box, well, all I have to do is say what things are touching the box because everything that's touching it is going to exert a contact force on it. And then in addition to the things that are touching it, there are these possibilities over here. Most likely it's going to be gravity, unless this box is floating on a table in outer space, right? So I look at my box, what's touching it? The table. So I would say that there's a normal force from the table. And now there's some air touching it, but like I mentioned earlier, you have to be moving through the air, so there's probably not much drag or air resistance on that box. Other than that, there is gravity. We're assuming this table is on Earth. So two forces acting on our box. Once we know what the forces are, we like to draw a simple little diagram known as a free body diagram. Oops. Undo. These are sometimes called force diagrams as well, same thing. And rather than just writing out the words, we usually abbreviate it and we use arrows to indicate the direction that the forces are going. Because forces are vector quantities, just like position, velocity, and acceleration. So the direction matters. Alright, my PowerPoint crashed on me there, so you might have noticed I had to redraw this and things jumped around a little bit maybe, but here we go. So I'll just go ahead and use these arrows here. So we have a force going up and a force going down. So there is my free body diagram, and we like to label these forces. The upward force is the normal force, so I'll do F sub n for the normal force. The downward force is F sub g for gravity. So nice, easy, simple force diagram or free body diagram for a box sitting on a table. Now if I have a box on a slanted line, let me go ahead and grab this line here. So a box on a ramp, let's say, and I'll just draw the box. Okay, box on a ramp, and we'll say it's stationary, not sliding down the ramp. And then if we think about the forces acting on this box, well, I still have gravity going down, and I still have a normal force from the ramp, but remember, normal means perpendicular, so it's coming straight out of that surface, not straight up. That didn't exactly work, did it? So somewhere about like that. And then we also have the force that's keeping it from sliding down the ramp, which would be friction. And now we'll label these forces, Fn for the normal force, Ff for friction, and Fg for gravity. And I don't really care exactly what letters you use. You can write it out if you'd like, as long as you're clearly communicating what you mean by your different forces. Let's look at one other situation real quickly and then we'll move on. Let's say that we have a wrecking ball and it is connected by its cable, its chain over here, and then maybe at night when they store it, they hook up a cable to connect it to some wall or something over here. So a ball with two cables, and it's stationary. Okay, so the forces acting on this, wow, that jumped right out. You're still going to have gravity acting down, and then you're going to have a force acting in the direction of each cable. So a rope or cable can only pull in the direction that it exists in. This guy won't be able to pull down or anything like that. Alright, so let's label these. The downward force is gravity. I have two different tensions, so I might call this guy T1 and this guy T2. So there you go. Each force, everything that's touching it, plus gravity, and the direction indicated by the arrows. Alright, so now that you've got an idea about free body diagrams, I'm going to do a little kind of a inquiry experiment with you here. So what I want you to do is to draw a grid like this on a piece of paper. Go ahead and pause the video. I'll be waiting. Okay, everybody got their paper. And what I want you to do is to draw some free body diagrams for me. The first row here, I want you to draw the forces acting on a car moving at a constant speed, constant velocity. Okay, so a car with cruise control traveling down the freeway, and the three boxes I want are at successive times, so maybe like at 1 second, a little bit later at 2 seconds, a little bit later at 3 seconds. Okay, so give me some arrows. I don't really care about the up-down arrows because those are going to be normal force and gravity pretty much every time. So really all I care about is what forces do you think are acting to the right, and we'll say that the car is moving to the right. Here's our car heading off in that direction. So what forces are acting on this car as it moves at a constant velocity? What forces to the right or left could possibly be acting? Okay, if you need to pause the video to fill that out, go ahead. Okay, the next one I want is a car also moving to the right, but this time I want it accelerating to the right, so it's speeding up. So again, what forces are acting? I don't care about the vertical ones. What forces are acting horizontally on a car that is speeding up? And are those forces changing over time, or are they the same as time ticks away? Okay. Alright, last one, and again pause it if you need to finish filling that out. Last one I want you to think about is a block of dry ice cruising along perfectly smoothly on a very smooth table. So again, we're at constant velocity, but nothing is touching the block of dry ice. It's melting or sublimating a little bit on the bottom, so that's why it has very little friction. And in fact, I want you to assume absolutely no friction in your three free body diagrams. No friction, but the block is moving to the right. What forces horizontally are acting on that block? Okay, you got it filled out. Pause it if you need more time. Here are the answers, and the reason why I wanted you to do this is if you ask somebody on the street, gave them a little 5-minute primer on free body diagrams and asked them to do this, 95% of the people would get it wrong. Even those who have had some physics training would get this wrong, and this really gets at the heart of Newton's laws. I'm going to start here with this block of dry ice. So there's basically no friction, so no force to the left, and you are not touching the block anymore, so all three of them should essentially be blank. I guess if you drew your vertical forces, you could have gravity and normal force. But there is no force to the right making it move. It keeps moving because there is no force to the left stopping it. So if we realize that, then if we think about the car, we should relate this idea that no horizontal forces means constant velocity. Well, with a car, there's obviously going to be some drag or friction slowing it down, which means there's got to be a force keeping it going. What most people do is they put this force larger than that force. Whoa, why did that erase? I don't know. But it turns out that to keep moving at a constant velocity, these forces here just need to be equal to each other. And they don't need to grow or shrink in order for that car to keep going. Looks like I made him grow a little bit. Sorry. But we get a picture that looks something like this, where constant velocity means the forces are either not there at all, or they are exactly the same size so that they cancel out. We call this balanced forces. Okay, when it's accelerating, there is still going to be some friction and drag pushing it to the left, but the force to the right now has to be larger in order for it to accelerate. But what most people do is they say, oh, if I'm speeding up, this force here needs to get bigger and bigger. The imbalance needs to grow. Well, that's not true. As long as there is any imbalance at all, even if it's minuscule, that object will continue to accelerate and continue to accelerate. Now, we don't experience that too often in our everyday experiences, because normally as you go faster and faster, these drag forces grow, and there comes a point where you can't exert any more force this way to overcome that growing drag force. And so there's usually a limit. Cars have top speeds because of this. If there was no air resistance or friction of any sort, a car could just keep going faster and faster. Well, granted, it needs friction to go forward, but if you imagine a rocket in outer space, as long as you can keep firing those rockets, your spaceship will go faster and faster. And that's why our spaceships do achieve speeds of like 20,000 miles per hour, because there's nothing to slow it down. As long as we're burning those rockets, we just go faster and faster. So these principles are really at the heart of Newton's laws, and definitely not what people pre-Newton thought. They thought if you throw an object, it stops because you gave it impetus when you threw it, and that impetus eventually kind of runs out of gas. Well, in Newton's perspective, it stops because you're no longer pushing it, and friction and air resistance are stopping it. But if you were in outer space and you threw a golf ball or something, it would just keep going forever and ever and ever, because there's nothing stopping it. Similar to this block of dry ice, it just kept moving, not because you were still magically pushing on it somehow, but because there was nothing stopping it. So if we summarize this, those principles are at the heart of Newton's first and second laws. First law, I like to call it the law of balanced forces. You might have heard people say for an object in motion will stay at motion, an object in rest will remain at rest unless acted upon by an outside force. That's all well and good, but it's kind of a mouthful. So whenever you have balanced forces, so that can be no forces or equal forces in opposite directions, then we always have an acceleration equal to 0. So this means you are either not moving at all, so stationary objects always have balanced forces, but it can mean that you are moving, and this is the tricky one. If you remember this, then you are smarter than much of the population, at a constant velocity. Okay. Second law says whenever you have unbalanced forces, then your acceleration is not equal to 0. And the amount of acceleration is given by the equation F equals ma, where F is force, m is the mass of the object, and a is the acceleration. So if we rearrange that and we think about how much acceleration we get, well, force is in the numerator, so bigger force, more acceleration. Mass is in the denominator, so larger, more massive object, less acceleration for a given force. And I should specify that the force we're talking about here is actually the net force, sometimes written F net, or sometimes it's written with a summation sign, meaning the sum of the forces. So that is the force we're talking about here. We have to look at all the forces acting on it and see what the result is, and given that force we can figure out the acceleration if we also know the mass. So this is the basics, and we will be looking at tons and tons of situations where you'll get to practice applying these wonderful principles from Sir Isaac Newton. See you next time.